Hi everyone, let us look at another interesting problem from integration. So firstly, I want to observe a few things over here. uh, that the differentiation of a ki power x with respect to x is nothing but a ki power x ln a, right? So the second derivative of a ki power x is nothing. I take ln a as a constant and I differentiate a ki power x once again. So the answer is gonna be a ki power x ln a ka whole square. Now I want you guys to observe that if I differentiate it once again, what I'm gonna get is a ki power x ln a ka whole cube. So I want you guys to notice the pattern over here. So once I differentiate it once, I get ln a ki power 1, and when I differentiate it once again I get square. So if I differentiate a ki power x n times, what I'm gonna get is a ki power x ln a ki power n, right? So this is what I wanted you guys to observe first. Now let us move on with the solution of this question. So what I'm gonna do is I'm going to take a function of n, that is j of n, and I'm going to define it to be equal to x ki power n dx, right? So now what I'm gonna do is I'm going to differentiate j once. So differentiation of j with respect to n. So what's gonna happen is the differentiation is gonna go inside the integral, and the differentiation of x ki power n is gonna be x ki power n times ln x. This is gonna be nothing but x ki power n ln x dx. Now what I'm gonna do is I'm going to differentiate j once again, and ln x is going to be treated as a constant, and the differentiation of x ki power n once again is going to be x ki power n ln x. So ln x is going to join with each other, and we are going to be left with nothing but x ki power n ln x ka whole square dx. So let's do once more. The third derivative of j with respect to n is going to be nothing but the integration from 0 to 1 of x ki power n ln x ka whole cube, right? So I can notice the pattern over here, right? So what I'm going to do is I'm going to keep on differentiating it, and after I differentiate this thing n times, so the nth derivative of j, that is going to be the nth derivative of j, uh, is going to be with respect to n is going to be nothing but the but the integral of x ki power n multiplied by ln x ki power n dx. And now you need to notice that this is nothing but the integration from 0 to 1 of x ln x ki power n dx. And if I replace n is equal to 100 over here, I'm going to be left with nothing but the question that we have been asked, right? So what I'm gonna do now is all I have to find is the LHS, and I'm gonna be done once I replace n is equal to 100, because this is exactly what we need in the question. So what is the nth derivative of j? Notice j we have defined to be equal to x ki power n dx. Now this whole thing over here is nothing. So I'm going to rewrite this by expanding it. Is going to be d of dn of d of dn of d of dn dot 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 of d of dn of nothing but the integral from 0 to 1 of x ki power n dx, right? uh, and this whole differentiation is going to be n times. So what I can do here is I can first compute the integral and then I can start differentiating. So I'm going to go from inside to outside, right? So the integration of x ki power n dx from 0 to 1 is going to be nothing but x ki power n plus 1 over n plus 1, which is from 0 to 1, which is going to be nothing but 1 upon n plus 1. Therefore, the nth derivative of j of n, and j of n is nothing but 1 upon n plus 1. So let's see, j of n is 1 upon n plus 1. Once I differentiate j of n once, I get nothing, this is nothing but n plus 1 ki power minus 1, right? So once I differentiate it, I am going to get nothing but minus 1 upon n plus 1 ka square. So similarly, what I'm going to do is I'm going to differentiate it once again. So the differentiation of this thing over here is going to be nothing but minus 1 multiplied by minus 2 upon n plus 1 ka cube, right? So what I'm going to do is I'm going to compute the third derivative of n now, which is going to be nothing but minus 1 multiplied by minus 2 multiplied by minus 3 divided by n plus 1 ki power 4. Now notice what is happening over here is once I differentiate it 3 times, this whole thing over here is 1 more than that. And this is nothing but the negative times the multiplication of the number of derivatives that we have, right? So I can generalize this formula altogether. The nth derivative of j is going to be nothing but minus 1 times minus 2 times minus 3 dot 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 times minus n divided by n plus 1 ki power n plus 1. Now notice what I had to do was I had to replace. Now this is nothing. Jn of n is nothing but the integration from 0 to 1 of x ln x ki power n dx. So what I'm going to do is I'm going to replace n is equal to 100 here, n is equal to 100 here, and I'm going to get the final answer to this question, which is going to be nothing. Let me add some space here. So that is going to be nothing but the integration of x ln x ki power 100 dx is going to be nothing but minus 1 multiplied by minus 2 multiplied by minus 3 dot 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 up to minus 100 upon 101 ki power 101. So I have substituted n is equal to 100 in this formula, right? So what I can see is there is an even number of minus sign here. So this is overall going to be a positive number. So this is going to be 1 into 2 into 3 up to 100. That is going to be nothing but 100 factorial upon 101 ki power 101, and that is the required answer to this problem, and hence we are finished. So this is a totally different approach that I wanted to show you guys, and you guys have to keep this in mind. This is a very difficult problem and a very different problem than what you guys might be exposed to in your regular classes.